Bismillah ar-Rahman ar-Rahim. Let's look at this problem. Determine the volume required. So he needs to know the volume. So he needs to find out the volume for a plug flow reactor to obtain the same degree of pollutant reduction. Okay? To get the same degree of pollutant reduction as the CMFR. An example 4.3. Okay? In example 4.3, the C out over Cn, the one it was shown before, it is 0.32%. So, to get the same degree of this, we need assume that the flow rate and the first order decay rate constant are unchanged. So the flow rate is 50 meter cubic per day, and K is 0.216 per day, and C out over Cn is 0.32. Now this is the plug flow reactor. Remember the plug flow reactor, C out or C final is equal to C initial or Cn e to the power minus K. Since he give you volume, he need to find out the volume, so we're gonna put T as volume over Q. Okay, now what is C out over Cn? C out over Cn is 0.32, so I'm gonna put 0.32 because C out over Cn is equal e to the power minus K. What's K? 0.216. So 0.216 times volume is unknown, okay, over Q. Look at Q is 50 meter cubic. Look at this, per day. So we have to make sure that the units are consistent. So 50 meter cube. So the volume gonna be in meter cube. Okay? So now let's do len. Len 0.32 is equal minus 0.216 volume over 50. Now, this is it. So len 0.32 times 50 over 0.216. And now I'm going to give you volume is equal 264 meter cube. So the volume for this plug for reactor that will give you the same treatment option 0.32 is 264 meter cube. This is expected because the plug flow reactor needed a small amount of volume, while in the CSTR or CMFR, look at this, 500 meter cubic. Okay, hopefully this is good to understand this problem. Let's go for the next slide. Now there is a lot of comparisons. If you want to compare between plug flow reactor and CSTR, there is a lot of research on the performance of these both reactors. Of course, the fluid entering the plug flow reactor travel downstream without mixing. Okay, this is the main difference between plug flow reactor and CSTR. There's no mixing; it moves downstream without mixing. The fluid entering the CSTR or the CMFR are immediately mixed. Okay, resulting in a low concentration in the reactor. So there is something without mixing, and there's something that immediately mixed for the CSTR, resulting in a very low concentration in the reactor, resulting in a low concentration of organics, of course, of organics. Okay, since the reaction rate is proportional to the concentration, first order or higher kinetics, the rate of reaction within the CSTR is reduced relative to the plug flow reactor. Also, CSTRs are easier to construct and operate from a treatment point of view. Of course, it's much easier to operate and to construct than plug flow reactor. And the performance of the CSTR can be improved by using multiple CSTRs. Remember when we saw that one CSTR might give you, let's see if this is in and out. Let's say that the input is 100 milligram per liter of any chemical name. And we did a reaction in this CSTR, and we got 5 milligram per liter. But the EPA told you that 5 milligram is not the guidelines. We need to make it close to 1. So we could do multiple CSTR. You take this 5 milligram, put it back in another CSTR, and then do the same reaction. Okay? And then you might get 1 milligram per liter. So sometimes we might have multiple CSTR in series. So sometimes you'll have 3 CSTR in series, depending on what is the removal, the final concentration of the pollutant that you want to get it off the treatment. So you can see that this is the multiple CSTRs in series. You can see the flow here is same as the flow out, which is going to be the same as the flow in, as the flow out, and as the flow in, and as the flow from the third one. So Q is equal to Q is equal to Q is equal to Q. Now, C initial, let's say A. CA1 out from here is going to be in for this one. And C out from this one going to be in for this one. And C out from this one is what's the final. So you could see that this 3 CSTR in series in order to reduce the concentration of the organics that will be disposed to even the open land or reused later on for agricultural reuse. So there's a lot of comparisons between plug flow reactor and CSTR response to inlet spikes, because in many pollution control systems, inlet concentration or flows may experience a sudden spike. You might have like high toxic chemicals in one time that's going to be suddenly come to the plant. So the reduction of the effect of spikes on outlet concentration can be minimized in CSTR. CSTR is very good in minimizing sudden spikes. Of course, the inlet concentration of the CSTR is diluted by the volume of the lower concentration of the fluid within the CSTR. CSTR are very good in controlling the sudden spike effect. So you could look at these if you want to look at between response to inlet spikes. But also we did talk about residence time, or sometimes they call it detention time, residence time, which is referred as the average time spent in a given control volume. So if you have a lake, and this lake has a river entering to the lake and another river coming from the lake, you can see that the time it took the water in the lake, how long it took the water to stay in the lake. And we call this detention time, or sometimes we call it residence time. This residence time is equal to the volume over Q. Of course, this Q has to be equal to this Q. If this Q is more than this Q, you'll have flooding. So you have to have Q in, Q out has to be the same. Theta is equal volume over Q. So you could determine what is the time of this water to stay inside these lakes or inside these tanks. Okay? Let's look at this. Here you need to find out the retention time in a CMFR as the example given before, and the plug flow reactor of the example 4.6 and 4.3. For the CMFR, remember the tank was like this. Okay? Q in and Q out are continuously going through the tank. Of course, there is water that will be there inside the tank. How long for this water to stay inside the CSTR before it goes out? This is what we call it retention time or residence time. So it's volume over Q. You have the volume of the CSTR and you have the Q, 10 days. So the water inside this CMFR will stay for 10 days before it goes out. For plug flow reactor, it's the same thing. Q in, Q out. and you can see that the time it takes the plug of water going from a place to a place is equal the volume over the flow rate. That's 5.3 days. You can see here it will take 5.3 days, and here take longer period of time. Retention time can be different when you compare lakes. These are the big, huge lakes that found in the U.S. Superior Lake, Michigan Lake, Huron Lake, Erie, and Ontario. The volume, each one of them is given here, 12,000 10 to the 9 meter cube and 4,900 10 to the 9 meter cube. And you have the volume for each. And of course, you have outflow, 10 to the 9 meter cube per year. Okay, let's find out the time. Time is by dividing volume over a Q. Look at this. Volume over a Q, and it's going to be in year. For the first one, it's 12,000. It's 10 to the 9, of course, it's going to cancel out, over 67. Okay, meter cube, you'll end up with year. Okay, so you can see from the first one, this cancel out with this, meter cube with this, you'll end up with year. So for Lake Michigan, the water will stay inside the lake for 136 years. Wow, this is an oldie water. So Lake Michigan, if you go and swim in Lake Michigan, you would expect that the water that you are swimming in, the age of that water is 136 years. Let's look at Lake Ontario. Volume over Q. You just get the volume. These are normal volumes. Look, Ontario, the volume is that much, and the outflow is 211. So this with this, you'll end up with the year going up 8 years. Oh, this water is really fresh. So, which means that if you're talking about the lake, the water inside the Ontario, the whole water system of the lake will be replaced every 8 years. We'll have a new fresh water coming into the Lake Ontario every 8 years. So this is every 136 years, and this is every 8 years for Lake Ontario. Of course, lakes are generally mixed twice per year because of the winds, because of, like you would expect, the oxygen entering the lake, the waves of the lakes. So these waves will really generally mix all the constituents of the water in the lakes. Okay, so we will be going to the next slide. Now, to calculate the average flux density of phosphorus downstream to the wastewater discharge. This is the average flux density is also another approach of determining how the movement of the waste downstream of the wastewater discharge of the example in 4.2. Of course, the cross-sectional area of the river is 30 meters square. And of course, in the example in 4.2, you can see that the Q is 26 meter cube per second. And the downstream concentration, 0.2 milligram per liter. The average river velocity is Q over A. You have Q, and you have the area of the river. So the velocity is 0.8. The velocity is 0.8 meter per second. So we are using the definition of the flux density. You can see how this is different from mass loading. By doing the flux density, you could multiply the concentration, 0.2 milligram per liter. Of course, you can convert the liter to meter cube because we need meter cube for later on. Times, you can see why we need that, liter with liter. So, times the velocity. Velocity is 0.87 meter per second. So, like this, the velocity is meter, you could leave it with meter cube, is meter square, and then it's going to be milligram, and you could convert milligram to, or milligram per meter square per second. So 0.2 times 1000 times 0.07. So we could see right now from this equation that the average flux density of phosphorus downstream of the wastewater charge is equal to 174 milligram per meter square second. You could do it from milligram to gram, it will be 0.17, almost gram per meter square per second. So this is what will happen with using the flux equation. And also if you look at this, you can see the way that the movement, if you have, for example, at time 0, if there is a membrane and 20 molecules of Y and 10 molecules of X in both sides, you can see sometimes the diffusion between these compartments, that 2 molecules of X is entered, okay, while 16 molecules of Y stayed. While here, 4 molecules of Y, the total, of course, the total gonna be 20. While here, 10 molecules of X remained from 10 molecules of X. So the diffusion and the movement between one compartment to another is what's determined this equation. Now, so why we have to study the diffusion coefficient and molecular diffusion? Because every compound has a molecular diffusion coefficient in water and in air. So for example, let's look at methanol, which means that this is the movement, the diffusion movement of this methanol in water. At 15 Celsius, its diffusion coefficient 1.26 10 to the minus 5 centimeters square per second. Same thing for ethanol in water, 1 10 to the minus 5. Acetic acid in water, 1.19 10 to the minus 5. Ethyl benzene in water, 8.1 10 to the minus 6. And CO2 in air, 0.151. Okay. So this problem will teach you how to understand how to apply the molecular diffusion of compounds. Let's see the transport of PCBs from the atmosphere into the Great Lakes. This is very dangerous. Into the Great Lakes is of concern because of health impact of aquatic life and on people and wildlife that eat fish from the lakes. PCB transport is limited by molecular diffusion across a thin stagnant film at the surface of the lake. As shown in figure 412, you can see the figure 412. This is the water. This is the partition between, this is the ocean. Here is the ocean. And this is the air. This is the surface of the ocean, and that's the air in top. And you can see that this is the stagnant film we're talking about. And then the concentration air will be at that side. Okay? So he said that, okay, stagnant film at the surface of the lake, as shown in figure 420, calculate the flux density. He needs to find out the flux density J and the total annual amount of PCBs deposited into the lake superior if the transport is by molecular diffusion. As he said, he has PCB in air, and he want to know, he want to find out the flux density J, and he want to know how much the annual amount of PCB that being deposited into the lake superior. Okay, the PCB concentration in the air just above the lake surface is 10 to the minus 12 gram per meter cube. This is in air. Okay, and the concentration at height of 2 centimeters above the water. This is the thin stagnant film. At height, the concentration at height 2 centimeters above the water surface is 450 10 to the minus 12. The diffusion coefficient for PCB is equal to 0.044. And the surface area of the lake superior is 8.2 10 to the minus 10. Of course, the BCB concentration in the air at the air-water interface, okay, is determined by Henry's law constant, because here, between the interface, it's Henry law constant. That's why you should do it as KH is equal C air over C water. And of course, we have to take the Henry law constant of this diffusion limited stagnant film. Okay, let's find out first of all the change of concentration over time. Now, we have the concentration just above the lake surface, 100 10 to the minus 12. The concentration 2 centimeters above the water surface, 450. So 450 10 to the minus 12, this is DC, change of concentration, minus 100, divided by, remember, it's the 450 is 2 centimeters. So this is 2 centimeters from here to here, over 2 centimeters minus 0, and that will give you, of course, you have to convert, this is meters and this is centimeter, so you have to convert centimeter to meter, so you can cancel out meter with meter, and you'll end up with 1.8 10 to the minus 8 gram per meter to the 4. Now, the flux and density is equal to J minus D, dC over dZ. Now, dC over dZ is equal to this. And the diffusivity is also was given, the diffusivity constant was given here as 0.044. This is the diffusion coefficient. So minus 0.044 times this, and then changing, since this is centimeter and this is meter, changing centimeter to meter square, so you can cancel out this with this. And also the same thing, second, and this is, if you want it in years, so you have to convert second to year, and this is down, so you make it up, so you end up with minus 2.4 10 to the minus 6 gram per meter square per year. This is the flux density. Of course, this negative sign indicates that the flux is downward, because the flux is going down toward the ocean. Remember, he was talking about, this is the water, whether it's an ocean or the lake, and this is the air. Remember, it's going down like this and then going up straight line, and this is Henry law constant is applied to the 2 centimeter above. And look at this. This flux, that, if it's a minus, mean it's going downward. It's going toward the water from the air. If it's plus, it's going to go the other side. So this is the downward flux. So this is to remember that now at the end, this is the first part of the problem. Now let's go and find out the total deposition. Now we find out the flux. We need to know how much is going down to the water. So if you multiply J times A, you could find out the total depositional flux. Okay, J is minus 2.4 10 to the minus 6 gram per meter square per year times the area. The area is 8.2 10 to the 10. Remember, it was given here that the area of the lake superior is 8.2 times 10 to the 10. So this would give you minus 2 10 to the 5 gram per year. This is how much deposits are going down to the water. You could make it, if it's minus 2 10 to the 5 gram per year, you can see gram per kilogram, and then kilogram per ton. Okay, so if you take 1,000, that's 2. If you take 1,000, and that's minus 0.2 ton per year. That's a lot of the position of PCBs into the Lake Superior from the atmosphere. And you could see that this is an extremely, it's too much a year of such a dangerous chemical. Okay, since we are doing this diffusion flux, now let's talk about dispersion. If you are assuming that if you have rocks there and the water is moving through these rocks, okay, let's assume that you have two fluid parcels starting near each other at location B and C at the end, and they will be dispersed. One of them going to go to the left and one of them going to go to the right to a location, different location, B dash and C dash. Of course, this movement is due to transport through the soil pores. While parcel A and B, sometimes they are far from each other, but the outlet are coming closer together, resulting in a mixing of water from two regions. This is what I mean by the process of mechanical dispersion. Sometimes the water are far away from each other, but they come at the end to mix at the same side. And sometimes they are close to each other, but they will disperse far away from each other. Okay? This is the last slide in this chapter. And Stokes law, and that's what we're going to be talking about in the next chapter 5. But let's assume that there is an air particle. And this air particle are settling in air toward the ground. Okay, this is the ground. And this is the particle. What are the forces that might affect this settling velocity of the particle? You can see the gravity, force of gravity down, force of buoyancy of the fluid. Of course, the fluid here is air. And force of drag. Okay? So whether this particle is in air or whether this particle is in fluid. So these are the forces: force of buoyancy and force of drag and force of gravity. These are the only forces. We'll be talking about this type of questions later on in chapter number 5.